Hi and welcome to video 14, Unit 1, Topic 3, Vector Proofs. So this is the second part of our vector proof video, and if you haven't watched video 13, it's probably worth a look. Just goes through some back-end geometric rules that you need to be aware of. But let's move on to some vector proofs work. So we have some definitions. I've written them all out here. I'm not going to write them as I talk. You can have a read of them. You might want to pause and have a read of them now. The definitions are, the first one is collinearity. So 3 points or more are collinear if a single straight line can pass through them. 2 points are always collinear because there's always a line that can pass through them. So you've got the red, purple and green point there, and they are on one single straight line, therefore they are considered collinear points. 2 are concurrent points. 3 or more straight lines are said to be concurrent if they meet at a single point. So you can see the red, green and purple line. Whereas if I draw this orange line, you'll see that it is not concurrent with the red, green and purple lines. And if concurrency, we're normally talking about 3 points as a minimum, and so often it is 3 points. The orange line meets the purple, green and will eventually meet the red line, but never two of them at the same time. So it's got no concurrency with the other lines. You'll also need to recall that two vectors are parallel if A equals K times B, where K is just a number, so K is a scalar. So what we're saying here is that if A and B are parallel, here's A and here's B, the only difference between them is potentially the length. And so that's the magnitude, but not the direction. And so it's the changing the components of a vector that change the direction, or maybe changing the angle in polar form. But if we just multiply by a scalar, that just changes the length. So if I can show that B is equal to 2 times A, well, that proves to me that B and A are parallel because the angle or the components haven't changed, but the length has. So dot point 2, if AB, so remember this is a different vector notation and really important for this geometric proofs section. If AB is parallel to BC, well then AB is equal to K, some number, times BC. And because B exists in both of them, so we've got A, B, and then, so I'll just dot that, and then BC, and you can prove that they are parallel, and you also know that B is in both vectors, well then we have 3 collinear points. So just keep that in mind. We can prove that collinearity by showing that pairs of vectors are parallel and that there's a common point within that vector definition. 2 vectors A and B, this is the third dot point now. 2 vectors A and B are perpendicular if and only if the dot product is 0. So that has to be true. To prove perpendicularity, show the dot product 0, or if you know they're perpendicular, then you know the dot product is 0. A dot A is equal to the magnitude of A squared. Just a little fact that you can prove quite easily. It's just definitely worth knowing. And here's another one that's really important, particularly for one of the examples coming up, and that is this linear dependence. So I'll just create a bit of space, and you can see example 1 there, but let's talk about this linear dependence for a moment. If we've got vector A and vector B, so this is A and this is B, and we add together a group of A's and B's. So we've got A to A to A to A to A to A. So I'm adding 3A, and then I'm adding to that 2B. And here is my resultant vector. So 3A plus 2B goes to there. Now, if this vector here, which I'll call C, is equivalent to some other vector, whatever it is, well then it must still be 3A plus 2B. The only way to get vector C out of A's and B's is by doing 3A plus 2B. For example, if I go to here, I only do 2A, which takes me to here, I can never get to that point using B's now because B's will only go in this direction. Or if I do 4A's, I can never get to that point. The only way I can ever get to that point is by using exactly 3A's. And then from the end of my 3A's, the only way I can get to that point is by then adding 2B's. So vector C only comes from that exact linear combination of A's and B's. And so if you have 2 equivalent vectors, made up of A's and B's, well then that means that the coefficient of A must be the same. M must equal P. And the coefficient of B, N must equal Q. And so we have this, it's called linear combinations and equivalencies within linear combinations, and we can use them to solve many algebraic situations. Okay, so there's the main points. Now, I wouldn't go ahead and try and memorize all those or anything like that. And there are some other minor points you'll need to recall, but certainly maybe refer to this list occasionally as you're doing the work. So what we're going to do is have a look at an example, and I'm going to split this up into two parts. So I'll do example 1 now, and then I'll do example 2 and 3 in a subsequent video. So here's example 1. It's a bit easier. In the diagram, AB is equal to X, so I'll make some notes as we go. So this is X, and BC is equal to Y. So this is Y. Determine CA in terms of X and Y. So this is A. So to go from C to A, keep in mind Y is there because Y is BC. I have to travel this way, and then I have to travel this way. That's the only way that is defined to me. I want to travel along the CA route, but I don't know the value of CA. But I can see that I've got to go backwards Y, and then forwards, and then backwards X. So when you get from CA, the vector is negative Y minus X. Okay, so that's the first thing. The second thing, let D be the midpoint of AB. So D is just here, and it's the midpoint of AB, and E is the midpoint of BC. So E is here. Right where I'll put these R's. Prove that 2 times DE is equal to AC. 2 times DE is equal to AC. So I'm going to draw DE there, and I'm talking about the magnitudes. And prove therefore that DE is parallel to AC. So remember, DE is parallel to AC, implies that we need to show that DE is equal to K times AC. And we already know that the magnitude of DE and AC are the same, so really all we have to do is show that they're parallel. And that's the next trick. If we can show that they are parallel, then we're good. And to show they're parallel, we're just got to show this. But let's start with the first part. The first part is to recognise, and of course we're dealing with DE and AC now. So let's define AC, we know, it's the opposite to CA. So it's X plus Y. And DE, let's see if we can work out DE. Now remember we've got midpoints here, so I'll just annotate in black. This is half X, and this is half Y. So how do we get from D to E? DE is equal to half X plus half Y. So there's our AC and DE. So then we want to show that DE is half of AC. So we say, well, this is equal to half X plus Y. And then we can write that down as a half AC. Now, this proves that they are parallel, and that K equals a half for that parallel relationship. But also I can now take the magnitude. DE is equal to, and a half is a scalar, it doesn't affect anything, half AC, and so I can double both sides. DE is equal to AC. And of course I've just shown that DE is indeed parallel to AC. Okay, so there's our answer to B and A for this fairly scaffolded question, which actually seems trivial. So you've got to be careful with maths sometimes, particularly in specialist maths. We don't assume the trivial. Well, we can look at that and go, well, it's pretty obvious. But by breaking it down using these two lines, the definition of AC and the definition of DE, we can prove that it's definitely true. So join me in the next video where we're going to look at 2 more further examples. And the second one of those is pretty tough, which means it's a good example for you to learn about. All the best.